Okay, now we're going to discuss the properties of alkanes, alkenes, alkynes, and even our aromatic hydrocarbons. So remember, we have just a quick review: alkane, alkene, alkyne, and these are our aromatic hydrocarbons. So let's take a quick look at their properties. What are their boiling points like? Are they really low? Are they really high? So let's see that. So there are a lot of words here, but we're going to go through these step by step, and I'll point out the most important information for us to know. So the first thing was that these are all nonpolar, and that's because they just have carbon-hydrogen bonds. And carbon and hydrogen are not very electronegative, and so they're just nonpolar. There's no polarity. I can't draw one of the dipole moments pointing towards the more electronegative atom. And so because they are nonpolar, we talked about how like dissolves like. They're going to want to dissolve in other nonpolar things. So if you're asked, does an alkane, which is nonpolar, would it like to be dissolved in water? We talked about how water is polar. So a nonpolar substance would not want to dissolve in water, but instead it would want to dissolve in other nonpolar substance. Doesn't dissolve in water. Okay, so now here's kind of the key information for us to know. It's that we might have, so we saw that we can have an alkane, which is just single bond. So let's first just discuss alkanes. And that's if we have a single bond like this and we have hydrogens drawn in. So actually, let's just draw this as that. So now we have 3 carbons, 1, 2, 3. Now for alkanes, as we increase the number of carbons, we are actually going to be increasing in boiling point. The reason for that is because there is an intermolecular force, which is referring to the forces that are between the molecules that are the same. So we should just do a quick little talk about what are the different intermolecular forces. So there are 3 intermolecular forces, 3 different possible types. The first one is hydrogen bonding, which is the strongest type. And that is when you have an electronegative atom, or if you have an electronegative atom like oxygen, nitrogen, and fluorine bound to hydrogen. So anytime you have those situations, you have hydrogen bonding. Now here we just have carbons bound to hydrogens. So a carbon is not an electronegative element like fluorine, oxygen, or nitrogen, so we don't have hydrogen bonding. The second type of intermolecular force is dipole-dipole. And right in the name, we mentioned that polar molecules have dipole moments. Overall dipole, which is shown by this. So an example of a polar molecule would be HCl. So chlorine is an electronegative element. It's close to the top right of the periodic table. So we can draw the delta negative symbol, whereas hydrogen is delta positive. And so I can draw this dipole moment pointing towards the chlorine because it is electronegative. So we get a dipole moment, meaning that this molecule is polar, and so the type of forces it has, we call those dipole-dipole intermolecular forces. So these are for polar molecules. Now the last type of intermolecular forces that's possible, they're called London dispersion forces, which is written out here. And this is just encompasses all the other atoms. So something that just has carbons and hydrogens, it's not polar. It doesn't have hydrogen bonding because there's no there's not one of these electronegative atoms bound to hydrogen. So all it has is London dispersion forces, which are the weakest. So it goes from strongest to weakest in that order. And so something about London dispersion forces is that the more carbons and the bigger the molecule is, the more London dispersion forces there are. So that's just a rule. And that's why as the molecule gets bigger, there are stronger London dispersion forces. There's more of those forces holding molecules together. And so it takes more energy to break those molecules apart. So as London dispersion forces increases, it takes more energy to break those apart. And that's why we have to put in more energy. So that's why boiling point increases as the alkane gets longer. Now, I just want to let you guys know this isn't usually extremely tested on, but it is good for us to understand, and your teacher might test you on this, so that's why I'm still going over it. Okay, so let's just look at that in a table so we can for sure make sure we understand this. So we'll see that these are the names of the different alkanes, so we'll soon be getting familiar with those, but For now, let's just look at the number of carbons. So as I increase the number of carbons, we just mentioned that the London dispersion forces are getting stronger. And so the boiling point is going to increase. Why? Again, because the forces are stronger. So if we're trying to break those apart, so in the case of boiling, we're trying to go from a liquid to a gas. So we're trying to break the molecules apart to make them a gas. And so we're going to need to put in more energy as the forces are stronger. So that's why the boiling point, we can see it getting higher and higher and higher. And melting point follows a very similar trend. So melting point is just you're trying to melt the molecules, so you're going from a solid to liquid. It still requires putting in heat, and the stronger the bonds are, so as you go down because you have more carbons, then you're going to need to put more heat in. So that's just a general trend to know. Melting point increases and boiling point increases as the alkane chain gets longer. Another thing to know about alkanes and their properties is that the more branches an alkane has off of it actually makes it have a lower boiling point. So the way that you can think of this is if you think of a tree, the trunk of it is very, very strong. So that's how we think of the parent chain or the main chain. So for example, this might be the main chain, but let's compare that to this molecule. So both of these have 1, 2, 3, 4, 5, 6 carbons. This one has 1, 2, 3, 4, 5, 6. Okay, so both of them have 6 carbons, but this one has a branch. So the main chain is here, 1, 2, 3, 4, 5, and it has this branch off of it, whereas this main chain is made up of 6 carbons. Okay, so branches make the boiling point weaker or lower. The reason for that is because if you think of a tree again, the trunk is like the main chain, and the branches are much easier to break off. Like think of a tree, as you go farther off and you're into the really small branches, they become really easy to break off. And it's very similar for a molecule. When you have branches, it becomes very easy to break apart. And so that's why we don't have to put in as much energy to break it apart. And so the boiling point is lower for alkanes with branches. So that's just a little thing to know. It's not that likely to be tested on. And from this part, it's just focus on understanding. So one thing to know is that if we compare, so up till now we were just talking about alkanes, which is just single bonds between carbons and hydrogens. Alkenes is when you have double bonds between carbon atoms. These will actually have lower boiling points than alkanes. And alkynes, which are when you have triple bonds between carbons, these will have higher boiling points than an alkane with the same number of carbons. And the reasoning is beyond the scope of this course, but just so if it helps you remember, the alkyne, because of its triple bond, it actually brings those carbons very close together, so they have a very high energy. And in order to break that high energy, you need to put in more energy, and so we need a higher boiling point to break that apart. But this is not as likely to be tested on. Okay, and now we've said we were going to talk a little bit about the aromatic hydrocarbons and their properties. So all you have to know is that they're pretty similar to the aliphatic hydrocarbons, so they have similar boiling points. And we mentioned that aromatic compounds are named this because they are aromatic and often have strong odors. This last point, we don't have to memorize this, but I just wanted to touch on this and explain this a little bit. So it says benzene is a liquid at room temperature. So what does that mean? That means that let's compare that to the alkane. So if we look at methane, its melting point, so when we go from a solid to a liquid, is negative 182.5 degrees Celsius. What does that mean? That means that at negative 182 degrees Celsius, it's melting into a liquid. Okay? So that means at room temperature at 25 degrees Celsius, it's probably going to be a gas, right? So methane gas, that's what it is at room temperature, because its boiling point is so low, right? So look at its boiling point, negative 161. So at room temperature, which is like, let's say 25 degrees Celsius, we're way higher than that. So methane is definitely going to be in a gas form. And that tells us that its bonds are very, very weak. And so we didn't need to input that much energy for it to boil. Whereas aromatic compounds have bonds that are slightly stronger because they're made with more carbons. And so they are liquid at room temperature. So they're not yet gas. So that's not something to memorize. I just wanted to kind of help us understand more about what melting point and boiling point mean. But as we go through the chapters, the properties are just going to help us understand the functional groups more, but the main thing we're going to be focusing on is naming, and that's also what your teachers will focus on the most on tests.